Officially welcome.
You can officially welcome.
All right,
Okay.
we'd like to welcome Gary Cole, who's come to visit UC San Diego from Nevada. He's going to talk today about upgrades to his Array Photo Polarimeter and the multi-band polarimetry capabilities that he's been developing. And this is all in the name of learning about new physics beyond the standard model with polarization measurements of distant galaxies. Thank you.
Hi. Anyway, as Andy said, for those who don't know me, I am an amateur astronomer, retired, not from amateur astronomy, from the software business. But I did once upon a time have an education in physics, for which I remember very little, and have always been kind of fascinated by polarization. So that's how I got into this as a hobby. And about, 3-4 years ago, one of Brian's grad students emailed me asking some questions about hardware, and that ended up with me coming and visit and doing a little bit of observation. So anyway, what I have is a backyard in Reno, Nevada, which has some telescopes in it. Now, as I like to joke with friends, the back two, those are Andy's telescopes. The little 5-inch in the foreground, that's the one I get to look through. So just so you understand the priorities here. This collection of equipment in one form or another has been out here for about, 7 or 8 years, more or less, looking like it does now. Although the patio blocks are new this spring, so that's been the major progress. Our weather has been horrible, so it gave me something useful to do at least.
Does that hurt? Will the heat dries enough in them at night time or not?
No. No, they're covered over with big sort of canvas covers during the wet weather. But other than that, they just sit out. And of course, they get to ambient pretty well as the temperature comes down. We do get, of course, we're high desert, so we get substantial temperature swings during the day, about 40 degrees midday to midnight. So it can be substantial. But it all manages to work. Okay. Now, what I'm going to first talk about is a little bit about the change in this system from what it was 2 years ago when we took data for the paper that we got finally published this spring. The original idea was to take account of the unique characteristic of polarization, which is that you essentially have to make two measurements, Q and U plane, in order to resolve the vector. And it occurred to me, I don't know, maybe half a dozen years ago, that there's no particular reason why you need to do that with one telescope, even though that is like the normal way of doing it. And so I sort of sat down and say, if I had two telescopes, I could shoot Q plane on one, U plane on the other, exactly the same time. And not only would we get it twice as fast, but there would be no delay between the measurements of the two angles. Therefore, we could be highly confident of the value of theta over time because we were measuring both aspects of it essentially simultaneously. Well, that was the original inspiration for putting two telescopes with polarimeters on them. Of course, things evolve a little bit. So this scope on the east side has always been a C14, and it contains a rather sophisticated back end. The first element here, which you can't see very well, is a unit called a waveplate carousel, which actually can put any one of 5 waveplates into position and then precisely rotate them under program control. That feeds into a 4-way instrument selector, which feeds downward into a camera, which serves as a polarimeter, and into basically 3 spectrographs that are on the other sides, which have in the past been spectropolarimeters at one time or another. At the moment, they're just sitting there. Okay. For the project that first got started some 3 years back, thanks to Dr. Tyler and Brian's input, we agreed that we really needed to get simultaneous photometry of these rather dim objects. And so I ended up putting a C8 on the top with another sensitive camera that works on about a 40 arc-minute field. So it gives a lot of choices of comparison stars. Now, we've never actually gone to the point of doing standardized photometry. We've just done it relative over the session of observation because we were looking for essentially changes in brightness along with changes in polarization. And so they could be reduced to standards. I just never bothered. The change I made over the last 2 years on this is, no, wrong button. On this is really fairly minor. All we really did was add a second C8 to the bottom. So now we can do 2 channels of whatever color might be of interest to you simultaneously. Now, understand that multiple telescopes sitting in the same backyard by themselves don't necessarily form any kind of an integrated observing system. So underneath all this is a rather elaborate software system, which I've been kind of evolving for about 12 years now, which not only chooses when to make the observation, but essentially kicks off parallel synchronized scripts into multiple telescopes, which run in parallel through I think 5 virtual machines now. So we have time synchronization between an exposure here, 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 actually also with the guiders, with the wide sky camera, and with the other telescope. And we're ending up with data sets that have images that are all within, whose midpoints are within a second or so of each other, which for 2-minute or so images seems perfectly reasonable for our problem. The other side started off as a C11. So this is about what it looked like 2 years ago. A C11 on a G11 mount with another one of these imaging polarimeters. Now these are kind of my own creation. They're very simple, nothing but a camera with a filter wheel which contains a Savart plate. And so the Savart plate can be pulled in and out of the light path. So the same camera can image on the target and center it, which is necessary given these are amateur scale mounts, and then can switch effectively into a dual beam polarization image. There's no collimating optics. These are just straight sky images that now have double stars everywhere. And the wave plate is as far upstream as we can get it, generally the first thing in the light path, as it should be before there's any 45-degree mirrors. Okay, this has changed in the last year, and that's what I'm going to talk about today, is the change in this and how it's been driven by Andy's requirements. It's now a subassembly, and this is really all one thing, which I call MULTIPOL. Well, maybe a hopeful description of it, but that's actually the intent. What MULTIPOL is a way to deal with the need to get delta theta, aka rho, which is a particularly difficult thing to measure, particularly with amateur telescopes. And I say that because one always hopes that professional telescopes are perfect in every way, and so I tend to think of the amateur ones as having all the problems. I have discovered some of the professional ones also are imperfect, but we'll leave that to illusion. The problem with measuring theta, when you're looking at changes in theta that are only a degree or two, is that it's very, very hard to get the wave plates, which are mechanical devices, in 2 separate telescopes that are floating around the sky at various times, always in motion, to be in a position that you can absolutely guarantee the dissertation committee were exactly right when you took the data. It's not that you can't align them, it's that you can't prove that they're aligned because over the 3 hours you're taking data, maybe something happened. So in order to say, I know that telescope's wave plate and this telescope's wave plates are consistent within, say, 1/10 of a degree, which is sort of what you need if you're talking about a 2-degree variation in theta, okay, 1/10, 1/4 degree, something like that. You are really pushing the limits of what you could reasonably expect. Now the wave plate rotators, for example, have a mechanical delta of about 1/10 of a degree. And there are 3 of them in the sequence between the 2 telescopes. So the result is you're dealing with kind of a 1/2 degree mechanical noise, so to speak, into the signal, even if you can get standard stars and everything else. Plus virtually any standard star measurement you're making, it's going to have an error of a couple 1/10 of a degree in theta. So it's really, really hard to bracket theta to better than a degree, and it's really hard to guarantee that you've kept it there over night after night of observations at different angles, temperatures, and everything else. So those are the things that came in mind when Andy started talking to me in January about, okay, we really want to have, slopes of theta as opposed to just, variation over time, which is sort of what we started doing. To deal with this, there are 2 solutions. One of them is you use dichroic filters. Take the light beam, split it by color filters, put cameras everywhere, get the light to go through a common Savart plate, a common wave plate, and then if your mechanics are all really good, you can pull multiple colors out without too much difficulty. Problem is you've now got a 25-pound assembly with 4 cameras, all of which have to be time synchronized to a fairly high precision, and a lot of very expensive glass. And I don't have a machine shop, so this adds to the problems. So I looked at, well, is there any other conceivable way you can pull this off? Getting multiple colors off one telescope, while letting the other one take still a 3rd color that we're a little less concerned about the theta relationship. And so I said, well, why not just build the world's worst spectropolarimeter? Now, I have some experience in this area. I've built two of them that we did a paper on some years ago. So at resolution 2000 and resolution 200. But this one's truly unique. I don't think there are any in the literature whose design resolution is 5. So what I'm doing is I'm using spectropolarimetrics for the purpose of getting broadband color separation, as opposed to learning about this polarization behavior of spectral features, which is the rational use of spectropolarimetry. All right? So that's the driving concept here. We build a very, very low resolution spectropolarimeter, and at the same time we do everything we possibly can to have its efficiency as high as possible. If you think of the typical efficiency of a filter-based polarimetric imaging chain, you've got a filter, and these, typical astrometric filters transmit 90% thereabouts, depending on your definition of the bandwidth you're really thinking about, and so on. And the cameras are typically sensitive, anything from 50 to 85%, depending on camera design and so on. So you're looking at net efficiencies in the high 70s typically. Here, the interaction between a blazed grating at its design wavelength and a camera whose QE peaks a little farther along gives us essentially almost a flat sensitivity curve between 5,000 and 7,000. And that just kind of works out that way, but it's a nice combination. Okay. The limit of what this can see is fundamentally defined by the wave plate, because it is only valid between a range, in the ones I use, are only valid between 425 and 750. So we really don't want any light outside that to be slipping in, because whatever polarization we measure will be slightly contaminated by improper half-wave rotation. Okay. This is a real simple-minded thing. Okay. This is a direct image spectrograph. That means that the light from the star hits the grating, hits the sensor, and every star in the field has a spectrum. Okay, so it's a mess in a certain sense. Okay, spectra can overlap stars, stars overlap spectra. The solution to that is twofold. One, make the spectra very small so they don't spread across too much field and essentially increase the probability of conflicts. But the key one is to put the whole assembly on a mechanical rotator. So essentially I can turn the star field to find a spot where my target star spectra doesn't interact with somebody else. And I suppose you could stare at star charts and figure out the correct angle. It's easier just to take pictures, find out what works and use it. So we have provision essentially for storing a relative angle for each object that will then present data which is absolute minimum of contamination from other target stars. So that's the reason for the rotators you're going to see in this stuff. The second problem is, for the work we did before at 14th magnitude, we were running 2-minute exposures in I and 2-minute exposures in luminance. Luminance is a great band. You get all the camera sensitivity, you get all the telescope's light in its best way, but you don't get much seriousness about where the band center is. And that's obviously a legitimate concern when you're looking at delta theta. So we wanted to go to narrower bands. Well, no matter how you do that, what you're also doing is you're going to less light. And so one of the problems which you probably never encounter, working with Keck and super friends, is that most amateur telescopes, SCTs, have a phenomenon called mirror flop, which basically means that the mirror, which is mounted so that it can be moved for focusing, moves very slightly as a function of the attitude of the system. It's somewhat reproducible, but you wouldn't want to bet on it. So the net result is, because of mirror flop, your exposure time is limited. And so 2 minutes is about as far as these scopes will go, even with an external guider, to stay essentially on pixel for the work. So if that works for luminance, how are we going to do B, or worse? Okay. And so the hardest problem here is actually long duration exposure, because we need to go out to at least 8 minutes to get similar net photon intensities we were getting in luminance. Okay, the way I finally settled on doing this after a couple tries is to use essentially a dichroic beam splitter. And these are commercially available units that are widely used in astrophotography these days. Essentially, all the visible light goes up, all the deep infrared goes out. And so this camera sees the whole field, about 16 arc minutes, but entirely in the infrared. And so it has to both plate solve on that, and then it does guiding on that. Meanwhile, essentially everything from 380 or so up to 750 goes that way. Okay? And of course, the wave plate rotator is here. We actually have some filters in front, although that's more of a calibration issue for this particular project than it is a data source. Okay, so keep that in mind. So on top of this, we now mount the multipole assembly, which consists of this physical rotator, which has a big 5-inch gear and rolls around at a couple degrees a second. And then the part that it turns, that is the part above this gear, is a Savart plate, a wedge prism, and a grating. Now, one of the goals, again, was to get the lowest dispersion possible. And that means using a low dispersion grating and getting as close to the sensor as you can. So I finally ended up physically mounting the grating inside the CCD camera. It's actually behind the cover plate, because I could get down to about a little less than 15 millimeters there. And that allows us to get the dispersion out to about 62 angstroms per pixel. Now, compare that to APPOL, the instrument down at the University of Arizona, okay, which is running at between 2 and 4 angstroms per pixel. So we're condensing 18 to 20 times more light, thus bringing a 14 up to the scale of a 2 meter and vice versa, while losing, of course, all the interesting spectral information, but that's the trade-off you make. Okay. So that's basically the design. And this then generates images on the CCD for whatever star has been selected to be in the right spot. Okay, so that's the physical hardware sitting in the yard. This thing is about, so by so, weighs about 14, 15 pounds. And that was first light, or something we will call first light. There are the spectra. They're 0.5 millimeter long. They're very cute. And they have very steep slopes, like so. This is the zero order star, because all we're really doing is taking a star image and dispersing it, creating effectively multiple copies of it. So as you see here, we've got what is actually a little over 4,000 angstroms that are being dispersed. The limit on this side is being caused by the dichroic. It actually extends out to about 9,300 or so that you could see in the spectrum. And the limit on this side is defined by the Balmer jump, essentially. See, I'm losing my voice here. Okay, unfiltered spectrum, pretty good from a light point of view. This is 11th magnitude star. So we're getting nice, strong spectra in a couple minutes exposure. The problem is, in order to divide, spectra A by spectra B, which is what you do for polarimetric analysis, you need to get these things really well aligned. And we're talking here very, very fine alignment compared to how you see them here. And that's kind of the problem. These are the three colors, purpose of discussion, we'd like to pull out of here. And you notice two of them have very sharp slopes associated with their data. The middle one's fairly easy to get. The other two are really difficult. You get artifacts from a polarization point of view that are essentially mechanical. So it's harder than it looks. Okay, so I had to ask myself, is this thing working at all? Obviously it makes spectra, that's easy, but is it doing polarimetry correctly? And I asked that because I never used a dichroic beam splitter before to put this together. And so I was concerned that perhaps we would get enough demodulation in that device to kind of really mess up the data. So I did kind of the obvious thing. I put a V filter on in front of the whole light path, and sure enough, out came two blobby stars, which is, in fact, from a spectrograph point of view, is the profile of that V light, modulated by this very, the seeing disk, essentially. Okay. Well, that looked pretty obvious, so I just put my polarimetric pipeline on that, and bibbidi-bobbidi-boo, out came 5.2% or something like that. It's a standard star, looked it up, that looks right. That clearly works. So I knew it was doing polarization correctly, even if I couldn't get the spectra to align without some more work. So then I did the same thing with a hydrogen alpha filter. So here, essentially, the width of the filter is actually less than a pixel. So everything you see is the profile, basically, of the star itself being expressed across the spectrum. But you can also see there's room for, a couple of these here. So we have really a couple fully separable colors. Well, at this point, what I've proven is that I can use an expensive beam separator, an expensive rotator, a grating, a prism, and a Savart plate to get basically the results that you can get with just a simple camera and a Savart plate, okay, with less efficiency. And you might be thinking, okay, what's the point of this talk? Why didn't he stay home this year? Okay, well, that's true. But the good part is when you do this, those star images can be processed with no concern at all for alignment. The things could be, the Savart could be twisted like this and the grating twisted like this. It wouldn't make any difference because what you've got are 2 star images, 2 photometric apertures, plink, polarization in one color. So how about if you used a 2-color filter? As far as I know, nobody ever did this before. This is a light pollution filter made for amateur astronomy, made by Astronomer. And you'll notice it creates 2 bands, one here in the high 400s and another one here dead center surrounding hydrogen alpha. Now for amateur astronomy, that's just great. And in particular, it absolutely kills everything below 600 and up to about 550, which is exactly where we have mercury, sodium, and a lot of the neon skylighting. And I live in a sort of a semi-urban area, so this is a big deal. So this thing not only gives you 2 separate band passes, it also completely kills the light pollution. If you look at where the wave plate falls, you'd be hard-pressed to design a filter that fit that wave plate any better. Okay? And there are actually 2 versions of it. This one, which has a short R band, and the other one where the red band is actually extended in the infrared, but it would be cut by the dichroic right where the wave plate cuts. So the net result is simply a wide R band. And for our purposes, we could use either. Okay. I actually have bought one of these. This one I probably pick up too, just to see how it works. So anyway, those are the 2 bands we can pull by doing nothing more than putting a filter in the light path. If you look at, compared to the Johnson bands, the wave plate has always been the problem here because it doesn't really get B. So I was saying to Andy back in the spring, if we use a B filter, we get about 1/6 of luminance light because we have to cut off about 2/3 of the B signal to match the wave plate. So we get a very poorly defined and small B. And R we have to cut off too because Johnson R has such an enormously long tail to it. So this wave plate fits these 2 bands really much better than the BVR system does and provides about as much separation as you could get between B and R. Okay, so what would you get when you put it in a spectrograph? Well, you get a double star. Now, the 0 order star would not be doubled. Excuse me for just being very simplistic about putting this slide together. Okay, so forget the double hump here. There's really just one. But the 2 signals, these are set properly on the actual dispersion. So this would be the 470 signal, and this would be the 660 signal. So that's what we should expect. And obviously one can change the grating distance, change the focal reducer a little bit, and so on, in order to merge or separate these 2 stars within reason, about as much as might be needed, in order to be able to get clean polarimetry on each star image separately. And that's what I'm intending to do. Okay, so having sort of discovered by serendipity and reading an advertisement, that filter, then the question, well, how do I evolve this thing to be useful to you folks? And one way is we could, of course, make this work. And that's entirely possible, but not necessarily a real quick project. I've debugged these before, and they take a while. The main task is we put in a secondary rotator so that the alignment of the vertical double star can be essentially made very, very exact. That gets rid of most of the alignment problems between those 2 steep curved profiles that you have to divide by each other. So that's the primary trick. And I've done this before with another instrument, so this will get you most of the way. Then you reduce the binning a little bit, because what you saw was at 3 times binning. So those were actually 200 angstroms per pixel. So you drop it back to 64, now you flatten the slopes, and the alignment should work out reasonably well. And I will probably someday get around to that. But it seems much more likely we just go and build a working 2-color polarimeter where we can use photopolarimetric pipeline on it, which we know works because we've debugged it over the last paper, among other things. And we also get a reduction in sky background and get rid of all these alignment problems. And that, that makes life much, much easier. So the simplest test, and this is what I'll do later this week probably, if the weather holds, is to just stick a filter in the light path and see what that double image really looks like. And as soon as I have one, I'll send you. So first light on this experiment is not far away. Filter should be home tomorrow. So, okay, that's probably not the optimal place to leave it. So it'll probably end up here where we can, in fact, pull it in and out of the light curve as desired. Now, if that works okay, then we'll probably find out that we want to separate the two star images more in order to get cleaner photometry of the two of them. And so I expect to pull back the grading and possibly put a focal reducer in. This, we'll just try all the combinations. It's all sitting in my backyard. It's fairly easy to do, to find the best place for it. And we could also then make this whole thing come in and out of the light path if we want to as a single assembly. So literally the grading and the Savart plate could be one thing, and we'll just feed it through whatever filter we wish. And if it all actually works, we go to the final step, switching cameras. So then we can plate solve in visible light and then just switch it into this mode and use this camera just to guide. So, because the plate solving in infrared is maybe not quite as reliable as the visible. So that is basically the scheme du jour, okay, for getting two colors on one telescope with no system-induced error into theta. Now, we still got photon error, we need long signals, we know all those things, but there's no reason to think that the delta thetas that come out of this will be limited by anything other than photons. And so long exposures, hopefully, will give us good results. There is a secondary thing to think about, though, is if we're using an 8-minute cadence on these things, how much is it going to turn while we're exposing? Okay, because as we found out on 714 on New Year's Eve a couple years ago, while the polarization of the blazar really didn't change over 3 hours, I watched the angle of polarization change by almost 100 degrees. I mean, literally, we were a degree a minute over 3 hours, which there are literature references for, so this was not just me being, unable to know what I'm doing, but kind of amazing. But a concern, because if we're measuring things on, let's say, a 32-minute photometric period, which is 8-minute exposure cycles, we might have 10, 15 degrees of rotation going on. And we wouldn't know it because it'll be averaged out by this whole process. Okay. So my thoughts, assuming we go and do this, my thoughts are that we'll run the eye side of this thing on the other telescope and stay on our existing 8-minute cycle. Run this one on 32. So we have similar levels of signals in all three bands. That's really the goal. Because then we can look at this and know whether it rotated while we were observing it. If it didn't, obviously we don't have to pay attention to it. If it did, we can arithmetically integrate this back to be compatible with the other one when we use the data. But I think it's probably better that we know it's turning than simply to be affected by it and never quite certain what happened because nobody else is measuring it. Okay, so this is basically my plan for the rest of the year. See if I can get this double star two color side to work and get a pipeline that produces results easily, and then merge it in array operation with the other scope. And that then brings us to is there anything you'd like me to look at? And that's really what I came here today to sort of find out. So that's basically what I came to talk about. And if anybody has any questions about this or some ideas to make it better, I greatly appreciate them. Thank you. And thank you, Brian. Okay. We done?
So yeah, that seems like a really interesting solution with the light pollution filters.
Yeah.
Given the constraints of the waveplate.
Mm-hmm. Yeah.
So hypothetically, if you were given the waveplate with the wireless sparing no expense.
I like that part.
What else would you be able to do?
Well, there's a company called Alexa, which makes dual band, tri-band, quad band, and pentaband filters just like this in a variety of combinations. So clearly you could get to 3 bands pretty much with off-the-shelf equipment and maybe more. Okay. I haven't seen one that has 2 bands in the infrared, except there's one at 600, 700, but Not sure we need to do that. Okay. One question I do have, and you folks who understand the analytics underneath all this, the IC band that we're using over on the West Scope basically runs 700 to 900 with most about 760 or 870 or so as being kind of mid-band points. But it's being strongly modulated by the response function of the camera. So the result is that band isn't 800 where you'd think it would be from its shape. It's really more like a 770 band or something like that. Now, we could force that by putting in one of these dichroic beam splitters, among other things, because it cuts at 750. Or by just using another blocking filter and push that band out at the expense of some light. So that's, if people think that it would make more sense to get a band that's out at 820 or something like that, like a Z filter band or a Z short band, that's perfectly within reason, not particularly difficult to do, at the expense of longer exposure. Now, we get the longer exposure by putting another one of these dichroic two-camera guider systems on the West Telescope, where I have a place for it, so that we could do 8-minute eye exposures. But then we lose the cadence measurement. So open trade-offs, and I'm open for anything people think is right. But I don't quite understand, your interest in the wideband stuff in terms of what sensitivity to where that third band really is. Because it can be as far in as 750, and we can push it out probably as far as 820 or 850 at some expensive light. So,
Yeah, I think,
I don't know.
The simplest thing is that we want an instantaneous measurement as instant as possible of the polarization angle versus wavelength slope.
Right.
And that when you're constraining these standard model extinction models, the wider the separation between those two filter bands midpoints,
Right.
the stronger your constraint, and also pushing it towards higher energy in the optical, towards bluer would be
Right.
helpful.
The problem is, as you know, anything below 400 is dying.
Yeah.
The atmosphere of the telescope, everything is dying. So this gets fairly close. This puts a band center at 470.
Yes.
And I kind of like those two bands. If we, just pop back to this. This is about as close as we can possibly get to the wave plate edge, okay? And yet the band's only 60 nanometers wide. So, we can compute the band center, modulating it with the camera function, probably have a band center that's good to plus or minus 5 nanometers, which, clearly that's the other factor in delta rho. It's not just photon statistics, it's how well do we know those band centers for the star of type. And I presume you've got SED information for this whole class of objects that we could use to figure out the modulation that the camera's applying.
Well, one of the strengths of the approach is that you're making conservative assumptions which make you insensitive to the source spectrum.
We hope so.
Yes.
Yeah.
So
Yeah.
that is something to look into.
Yeah.
The other point you raised, which is interesting, is definitely the question that on short time scales, the polarization angle will change.
Yeah, a lot.
And so essentially, let's say you had an 8-minute exposure, and then you have 2-color polarimetry, you're basically getting the time integrated version of this slope measurement.
Yeah,
Yes.
exactly.
And I think that clearly, if you had a huge telescope and you could do a really short exposure, you'd be less sensitive to the intrinsic changes. But I think that the nice thing about these standard model extension effects is that essentially what they would predict is that for an individual source, the distribution of slopes would be different over time, but that as you go toward higher redshift, the distribution of slopes would broaden as a function of redshift. And I think that would be true even with these time-integrated measurements.
Yeah, I don't see why they wouldn't. I mean, the main thing is we're getting absolute simultaneity, and there's no two cameras involved, no two different flat fields. It's all exactly the same image plane, and they're very close apart for that matter. A couple, no more than 50 pixels apart. So it seems to be a good solution.
The interesting extrapolation would be how well can you do as a function of telescope size?
Right.
And so that the idea of putting a system like this on a 1 or 2 meter class telescope, you could certainly you want to image as many high redshift galaxies as you can over different tight in the sky. And the whole idea is that you can do this much faster with a system
With
like
more
this
aperture,
than
yeah.
with a full spectral polarimeter, where,
Clearly, yeah.
where you're wasting a lot of the light for the purposes of these slope measurements. But it's an interesting question of whether you need 2 or 3 bands to get that slope measurement.
Well, we'll get one
Yes.
measurement off the two.
Yes.
We can say to ourselves, we know this is legit,
Yeah.
limited only by photons.
Mhm.
Then the question is, does the third one fit?
Does it
You know,
improve your measurement?
Can
of the
can we
slope?
believe that it's good enough that we can use it to further refine the slope or not?
Yeah.
We'll certainly get the wideband polarimetry anyway.
Yeah, I think it would give you a better slope measurement, but the question is the trade-off versus the amount of time it would take to get the exposure, amongst other things. To
I don't follow.
well, if you're splitting the light into 3 bands instead of 2,
Oh,
that's all I'm talking about.
That's certainly true.
Mhm.
I'm saying in this particular case, where we've got a separate light source that we're measuring, and the error is basically mechanical in terms of how well do we know theta from that source.
Mhm.
The other thing we could do, rather than running I out there, we could run V,
Mhm.
and so we essentially have 3 colors that ought to be in a fairly linear theta relationship.
Yeah.
So that's another way to test whether we've got some alignment.
Yes.
So, anyway, so that's all I